All right, hello everyone. We're gonna get started here. Going over stuff with chapter 6. I'm gonna pull up that diagram. Well, I'm gonna rewrite that diagram that we had earlier, or from last time. So we had mass. We have mass, moles, and particles. All right, this is an element. This is a compound. So grams of a given element. Moles of the element. And number of atoms. Okay, we can get between these two by using Avogadro's number, which is which says that 1 mole of any element is equivalent to 6.022 times 10 to the 23rd atoms. We can get between these two by using molar mass. And the molar mass is not something you have to have memorized. It's the mass from the periodic chart. All right, then we can also have some calculations for compounds. So we can have the mass of a compound, grams of compound. Moles of a compound. And we can have molecules. The difference really between here and here, I mean, it follows similar patterns, but the top flow chart is for a single element. The bottom one is for a compound. So this step here is the same as this Avogadro's number, except it tells us that 1 mole of the compound, whatever that compound happens to be, is equivalent to 6.022 times 10 to the 23rd molecules. Because what's the most basic particle of a compound? It's a single molecule. Or this can also be a formula unit. And when I say formula unit, I mean like NaCl or Al2SO43, something that is ionic. This step here is calculated by the molar mass of the compound, and you have to calculate that. So molar mass of compound. And the way you calculate that is you add all individual elements. So for instance, the molar mass of water, which is H2O, is going to be the mass of hydrogen, which is 1.01, times however many of them you have, which is 2, plus the oxygen, which is 16, and we have 1 of them. That gives us 2.02, and this gives us 16. We add those together, we get 18.02 roughly. And the unit on this is gram per mole, right? The gram gets stuck with the number. The mole is always in reference to 1. So let's do a problem with the compounds before we start to pair these things together. So say that we're given, we'll just use water since we already have the molar mass, that we have 3.52 times 10 to the 25th molecules of H2O. I want to know the mass of that in grams. So find grams of H2O. So looking at your flow chart, figure out where you're starting, where you're ending, and take the necessary steps. I'll give you guys 2 minutes to work through that one. Okay, so for this one, we are given the amount of molecules of a compound. So if I was to look at my flow chart, this is where my given information is sitting. I'm trying to find grams of the compound. So I want to end over here. So I need to take 2 hops or use 2 different conversion factors to get me from my starting point to my ending point. So start with our given information, which is this 3.52 times 10 to the 25th H2O molecules. And the first thing is to get it into moles. There's no direct way between molecule and gram. I've got to stop off in that mole crossroad. So I'm going to use my Avogadro's number. Since we are talking about the molecules, I want to put the big number molecule on the bottom. So that's 6.02 or 6.022 times 10 to the 23rd molecules. And that's going to be equivalent to 1 mole of water. Now that I'm in moles of water and the molecules have canceled, I want to get into grams. So this is where we use our molar mass, which we had calculated just the step before. All right. If mole is on top here, I'm going to put the mole portion of this on the bottom. So the 1 mole goes on the bottom. And how much does 1 mole of water weigh? It weighs 18 or 18.02 grams of H2O. That will allow me to cancel out my moles. So you're going to take your big number and you're going to divide it by a big number, and then you're going to multiply it by 18. And I'm just going to run my calculation one more time just to make sure I got that right. 58, yep. Okay, looks like I did it correctly. All right, so we've got 3 significant figures in the given information. So I'm going to round this to 1,050. And the unit on this is going to be grams of H2O. So I do really feel like this flow chart is helpful. We're going to connect these 2 things together now. So I'll pick a different color here. So let's put an arrow going this way and then an arrow going this way. Sorry, my Avogadro's number is sort of in the way, but it's between molecule and atoms. Let me make this number of molecules. Put like an X here, okay, or something here, because there is no direct way to go from gram of a compound into gram of an element. So that doesn't exist. If for instance, you were given gram of a compound and I wanted gram of an individual element, and we will totally practice this, you're going to have to go backtrack into moles to then flip back. Okay, so just put an X there for now. So what allows us to move back and forth between, let's say I had the moles of a compound and I wanted to know the moles of an individual element, like for instance, water here. The formula is H2O. How many moles of hydrogen are in it? Well, you're going to use the subscripts to tell you the number of moles. So give yourself a little note here that says subscripts from formula. In addition, it's also the same thing here, subscripts from formula. This one may feel a little more intuitive, right? Because hey, if I've got a single molecule, I'm going to have 2 hydrogen atoms and 1 oxygen atom. The same thing applies for a mole relationship. We can use the subscripts from the formula. So let me do a little bit of an analogy here with like 4-leaf clovers. So let's say, or 3-leaf clovers. Say we're going to calculate the number of leaves in 14 clovers. If these are 3-leaf clovers, you probably can just do the simple math and say, oh, well, obviously, there's 3 leaves. I'm going to take 3 and multiply it by however many clovers I have. Well, you may not realize that you're actually doing dimensional analysis there. What you're doing is you are comparing a whole to an individual part, right? So for every 1 clover, we're going to get 3 leaves, right? Or for every 1 clover, we also have 1 stem. So 3 leaves for 1 clover. If we have 14 clovers, we use that relationship of the whole to the part, 1 clover for every 3 leaves. Look at that. We're taking 14 times 3. We get 42 leaves. You probably just could do it in your head. But when we're dealing with compounds and stuff, I want you to set up in dimensional analysis. So other examples of combining or comparing a whole thing to its individual parts. 1 spider has 8 legs. These 2 things are equivalent to each other. It can't be a spider without having 8 legs. 1 chair has 4 legs. Okay. Can't be a chair without, well, I guess there are chairs out there that don't, but let's just say it's a traditional chair. 1 chair has 4 legs. So this allows us to jump from one thing to another pretty quickly, right? If I have 3 spiders, I can set it up in dimensional analysis and know that every spider has 8 legs. If I have 3 of them, there'll be 24 legs total, right? The same thing is true when we're looking at a molecule. If we look at 1 water molecule, it's going to have 2 hydrogen atoms. So what if I had 5 water molecules? Okay, if I had 5 water molecules, I'm going to have 10 hydrogen atoms because the subscript tells me how many hydrogens I get out of it. The same thing is true for moles. So carbon dioxide, compound that has 1 carbon and 2 oxygens. So I know that for every 1 CO2 molecule, I get 2 oxygen atoms. Similarly, if I had 1 dozen CO2 molecules, I'm going to have 2 dozen oxygen atoms, right? Because we're just taking our base here and we're multiplying it by a dozen. Well, the same exact thing applies for moles because remember, a mole is just like a dozen on steroids. So for every 1 mole of oxygen, I'm going to get, or rather, for every 1 mole of CO2, I'm going to get 2 moles of oxygen because the subscript says there's 2 of these things contained within each one of these things. So now we have a mole relationship. There's another relationship into this formula as well. The other one says that, hey, for every 1 mole of CO2, I need 1 mole of carbon, right? Or if we're dealing with this thing, for every 1 mole of carbon, it has to combine with 2 moles of oxygen. So these are all a variety of molar relationships. Let's try one that's a little bit more complicated. Doesn't get super complicated, but let's say. So write out the formula for aluminum sulfate. Aluminum sulfate. That's your nomenclature stuff. So remember, aluminum, Al, has a 3+ charge. Sulfate, SO4, will give us a 2- charge, and we're going to flip-flop. That means I end up with Al2, and then in parentheses, SO4, 3. So for one of these molecules, how many aluminum atoms do I get? The subscript tells me 2. So I get 2 aluminum atoms. How many sulfur atoms do I get? Well, sulfur's sitting here. There's one of them, but outside the parenthesis, there's a 3. So a total of 3 sulfur atoms. How many oxygen atoms do I get? Well, there's 4 within the parentheses and 3 outside for a total of 12. So I get 12 oxygen atoms. So this thing here is applying to this right here, jumping between the number of molecules and the number of atoms, because we have all these built-in conversions. I could easily take molecule and atoms and just replace it with the word mole. So 1 mole of Al2SO43 will contain 2 moles of aluminum. It needs 3 moles of sulfur, and it will require 12 moles of oxygen. So now I've got a conversion factor that allows me to go from the whole thing, like quote unquote, the clover, okay, to a part, like the leaf or leaves. Okay. This second one here is what we're seeing happening here between mole of compound and mole of element, the subscripts for the formula unit. So let's actually use aluminum sulfate, Al2SO4, 3. And we'll do a problem. I'm going to say that you are given given 32.5 moles of the aluminum sulfate, of the Al2SO4, 3. I want you to find the moles of oxygen. So how many moles of oxygen are contained in 32.5 moles of aluminum sulfate? I'm going to see if you can chew on that on your own. And start by writing out a relationship between moles of the compound and moles of what you're trying to find. We'll come back to you guys in 2 minutes or so. All right, so I want to come up with a relationship between aluminum sulfate and moles of aluminum. I don't have to make it up out of thin air. I don't have to have it memorized. I can just look at the formula here. And so I know that for every 1 mole of the compound, and the compound always gets the 1 mole, we just sort of default it as 1 mole. So 1 mole of the Al2SO4, 3, that's going to require 12 moles of oxygen. Okay, because the subscripts tell me that you get 12 oxygens in every 1 compound. I don't need to worry about aluminum and I don't need to worry about sulfur for this given problem because I'm not asking about aluminum and sulfur. So I start with the given information, which tells me, hey, I've got 32.5 moles of Al2SO4, 3. I want to move away from the amount of the compound and I want to get into the amount of the individual elements. So on our flow chart, we're starting here, we're ending here. Okay, so we want to move up the flow chart. The subscripts are what do that. That's this thing here. Let's put the 1 mole of the compound on the bottom because again, we want to get out of compound information. We want to get into individual elements. So the 12 gets put on the top. And specifically, it's 12 moles of oxygen. You want to start getting in the habit of like identifying your mole as a mole of something. So don't just say mole. Say it's moles of oxygen or moles of sulfur or moles of whatever compound, because especially when we get into chapter 8, 2 chapters from now, we're going to have moles of all sorts of different things. So the moles of the compound cancel here. And it just leaves us with moles of the element. And we have 3 sig figs, and I believe I got a whole number when I rounded that, right? 32.5 times 12 gives me 390 with 3 sig figs. I'll put a decimal here. What is the unit on it? It's moles of oxygen. It's not just moles of oxygen, okay? So make sure you're pairing it with something. How often are you given moles in real life? Never, okay? You're always given things, usually in grams. So instead of given a mole of a compound, because the scale can't pop out a mole value because it doesn't know what compound you're specifically talking about, but it can give you the gram. So if I give you the gram of the compound and I want to know, let's say, the gram of a given element, I have to do a 3-step problem. I have to go grams of the compound into moles of the compound, moles of the compound into moles of the element, and moles of the element into grams of the element. We kind of coil around. Some people will say, oh, well, can I go grams into moles and then moles into molecules and then molecules into atoms and then atoms into moles? You could, but that's an extra couple steps. So I would keep it tight right here. So let's try it out. Well, I'll do one for you guys, and then I'll have you work on one. And let's just do it for aluminum sulfate. Okay, we'll keep aluminum sulfate is what we're talking about. So let's say we have 14.75 grams of aluminum sulfate. And I want to know how many grams of sulfur is there. So I want to go from a mass amount of a compound, which is this thing here, to a mass amount of one of the elements, not all of them, just one of them. So I want to end up over here. So I need to coil through this. Now I'm going to unfold this and kind of make a flow chart for what we have. So we have grams of Al2SO4 3. The first step is I'm going to need to get it into moles of the compound. Moles of Al2SO4 3. Then from there, I can go into moles of the element, right? And what element am I talking about? Well, I'm talking about sulfur. So let's get moles of sulfur. We don't need to worry about oxygen. We don't need to worry about aluminum for this problem. After I get moles of sulfur, then I can work my way back into the gram value and get grams of sulfur. Now, you know how to do each one of these steps. It's just a matter of chaining them together. So this step right here, going from grams to moles of a compound, we need the molar mass of aluminum sulfate. So I'm gonna lazy girl this and just look it up on the internet. So molar mass of aluminum sulfate. Okay, and if you didn't know, Uncle Google has all the molar masses of like all the compounds. So if you start getting lazy, you can just say, hey, what's the molar mass of this thing? So the molar mass here is 342.15 grams per mole. All right, that stays in this spot here. What is the relationship between moles of the compound and moles of sulfur? That's this step here. That's going from here to here. So that's where we use the subscripts. So for this given problem, 1 mole of the Al2SO4 3 is going to yield how many moles of sulfur? Well, look at the subscript for sulfur. It is 3. So we're going to get 3 moles of sulfur. The last step is to go from moles of the element back into grams of the element. And this is simple. We just use the molar mass off the periodic chart. So for this step, we're going to use molar mass of sulfur, which is 32 again, I don't have my formula sheet with me. It's roughly 32 grams of sulfur per 1 mole of sulfur. So as you get the hang of it, do you have to write all these things out? No, but I want you to see like where my thought process is, so that if you do want to write it out, you can. So we start with our given information, which is this. We've got 14.7 5 grams of Al2SO4. Step 1 is to get from grams into moles. All right, well, gram is on top here, so gram needs to go on the bottom. So the 342.15 actually has to go on the bottom here, or we're going to divide by the molar mass. And this is grams of Al2SO4. That mass is equivalent to 1 mole of the Al2SO4. Okay. That got me into the first conversion. The second conversion, we're trying to get out of the moles of the compound. So I'm going to put that on the bottom, 1 mole of the Al2SO4. And I want to get into moles of my element that I'm talking about. In this case, it's sulfur. So we get 3 moles of sulfur. You can see the grams of the compound cancel, the moles of the compound cancel, and now we're in moles of sulfur. So we're at this point in the flow chart. We're here and or right here. We want to do one more step and get back into grams. This is where we're going to use the molar mass, but make sure you're using the molar mass for what you're talking about. We want to use the molar mass of sulfur, not of oxygen, not of the compound. For every 1 mole of sulfur, we get 32 grams of sulfur. That will allow the moles to cancel. And then you have to just plug this into your calculator. Sometimes people will go, for this last step, they'll be like, oh, but don't we have 3 moles of sulfur? So don't I want to put a 3 here? No, you've already taken that into account here. So you don't double that ratio up. We get our 14.75. I'm going to multiply it by a 1. I'm going to multiply it by a 3, multiply it by 32. And then the only thing in the denominator that is a divisor of any value is that 342.15. Okay. So I end up with a mass value of 4.139 grams of sulfur. You can ask yourself here, does that make sense conceptually? Yeah. If I've got 14.75 grams of a compound, I would expect one of the individual elements to weigh less than that, right? So 4.139 grams of sulfur, it sounds about right. If this number in mass ever becomes bigger than the mass number of the compound, something went awry. Okay, you multiplied it or divided incorrectly. So I'm going to give you another one of these. I'm going to squeak it in down here because I want to leave this up so you can kind of mirror the flow chart of it. But let's say we're given that we have 138.2 grams of, let's do something new. Let's do calcium nitrate, CaNO3, 2. Okay. I want you to find grams of oxygen. So if you like, create a customized flow chart like this. If I kind of made that make sense, feel free to just start your dimensional analysis. But I'm going to give you guys about 5 minutes for this one because these take a little bit long. Okay, so I'm going to erase the work for this one so that I have some space. Hopefully you're able to see that. So this problem, the setup it's identical to the one about aluminum sulfate. It's just a different compound and it's a different element you're trying to work towards. So you've got to change up your conversion factors, but the actual setup itself is the same. So my flow chart for this thing is going to be grams of CaNO3 2 into moles of CaNO3 2 into moles of what we're trying to find, which is oxygen, into grams of oxygen. All right, the molar mass, let's see, calcium nitrate. 164. So 164 grams for every 1 mole of the CaNO3 That goes in this step here. This step here, the relationship is, well, for every 1 mole of my compound, CaNO3 I'm going to get 6 moles of oxygen. Why is it 6? There's 3 on the inside of the parentheses multiplied by 2. So multiply those. And then this step here is just the molar mass of oxygen, which is 1 mole of oxygen is equivalent to 16 grams of oxygen. So we start our flow with our given information, 138.2 grams of CaNO3 Use the molar mass of the compound to get into moles. I want to get out of grams and I want to get into moles. So 1 mole of the CaNO3 is equivalent to 164 grams of the CaNO3. A really common mistake that I will see is people pair the number with the mole value. The number needs to be paired with the gram value. Okay, so make sure you're keeping those two together. Then we're going to use this relationship here that says for every 1 mole of my compound, which is CaNO3, I'm going to get 6 moles of oxygen. 6 moles of the oxygen. That's this step here, where I'm trying to figure out what is going on subscript wise. And then the last step is just to use the molar mass of the element we're talking about. Again, we want this crisscross cancellation. So the mole here needs to go on the bottom. 1 mole of oxygen for every 16 grams of oxygen, and those cancel. I never memorize these flow charts. I just kind of let it, well, I memorized the flow chart itself, these things, this concept, but I don't memorize like, oh, I divide or I multiply or what. I just let it cancel as needed. So we plug this in, I get 138.2. I'm going to multiply it by anything that matters on the top. So a 6 and a 16, and then divide it by anything on the bottom that has value, 164. And I get, we have 4 sig figs, so 80.90 is what I got, grams of oxygen. Look, if you got 80.91 or 80.88, that is more than close enough. Okay, I'm not going to be splitting hairs with these. If y'all can get this set up here, like that's what I'm going to be happy about. Okay, I'm not going to be testing you on silly little sig fig stuff at this point. So any questions on that, or how to work this flow chart? Because this flow chart makes up the first, like, say the first 75% of the chapter. This last little bit that we have to lecture on, I think it's going to feel refreshingly easy compared to this. Normally, in a classroom setting, you would not have this flow chart, but since you guys are taking class from home, you will get to use this. So have it available when you take the exam. Make sure though that you have some sort of reminder that you don't go directly from here to here. Questions? Okay, so we're gonna move into this concept called mass percent. If you started working on the lab at all this week, it talks about that. Okay. Hold on 1 second, sorry guys. Okay, so the mass percent composition or mass percent of an element is the element's percentage compared to the total mass of the compound. So this would be like if you've ever calculated your percent body fat. How is that calculated? You take the amount of your body that's fat, and you divide it by your total body's mass. And then you go ahead and multiply it by 100. And that gives you a percentage of how much of your body is fat. The same equation applies when we're doing a mass percent of a composition. We take them, let's say we have some hypothetical element X and it's included in a compound. If I want to find the mass percent of X, I'm going to take the mass of X in the sample. I'm going to divide it by the mass of the sample of the compound, and then I'm going to multiply it by 100. Pretty basic percentage problem. So let's look at a problem here. I have a 0.358 gram sample of chromium, okay, reacts with oxygen to produce 0.523 grams of a metal oxide. When they say metal oxide, they're just saying, hey, it's the chromium mixed with the oxygen. And chromium has a varying charge, so it's just not even getting into the charge. This is the total. This is the amount that's coming from the chromium. So if I want to find the mass percent of chromium, I need to take the mass of the thing I'm looking for, chromium, and I divide it by the total mass. 0.358 grams goes on the top, 0.523 grams goes on the bottom. And then we multiply it by 100. So what we end up getting here is 68.5% of this thing is chromium. The remaining, oh, my math today is so rough, 31.5% would be the oxygen, right? Because the total percentage needs to be 100. So you can solve this with experimental values. You can also come up with what's known as a theoretical mass percent. So if you have a formula, you can decide in theory what that percentage should be. I don't use this part here where we use mass percent as a conversion factor. I just think it kind of confuses people. If you want to learn it, it's another way to solve going through that flow chart, but I'm just going to skip over that. Okay, so let's say we have this formula here, CCl2F2, and I want to calculate the mass percent of chlorine based off of the chemical formula. I don't have any experimental data. I didn't run any sort of experiment. I just have a formula. So the way that I figure out the mass percent is I take the molar mass of the chlorine and I have to multiply it by 2 because there are in fact 2 of them. What's the molar mass of chlorine? 35.45, I believe. And we multiply it by 2. I'm going to divide it by the molar mass of the entire compound, right? This is sort of like the top is kind of like the fat in your body. The bottom is your total body. Okay, this is the element I'm looking for. This is the total thing. So I would take the mass of 1 carbon, 2 chlorines, and 2 fluorines. Carbon has a mass of what? 12.01, and there's 1 of them. Chlorine has a mass of 35.45, and I have 2 of them. Fluorine has a mass of 19, and I have 2 of them. So the total overall mass on this thing should be 12.01 plus 35.45 2 plus 19. 120.91 roughly. Now, the biggest mistake I see with this is that people don't multiply it by the subscript. They don't multiply it by the 2. They'll just put the 35.45. Do not do that. That will not work out. So we want to take our 35.45 and multiply it by 2, divide it by the total, which is 120.91. And then at the end of the day, we multiply it by 100. So the mass percent of this, 35.45 times 2, divided by the 120.91, and then multiply it by 100, gives us that the chlorine is roughly 58.6% of the sample. So majority of the sample is the chlorine. I want you to solve the mass percent for carbon and for fluorine. Okay, so you're going to do the same thing, except you're going to switch out the numerator. Instead of it being about chlorine, you're going to take into account the carbon, and then you'll do a second calculation and take into account the fluorine. And I'll give you all like 2 minutes for that. Okay, so if we want to do mass percent of carbon, we're going to take the mass of carbon, which is 12.01. We only need to multiply it by 1 because I only have 1 in the formula. And then I'm going to divide it by, I've already calculated the molar mass of the compound. It's this thing here. So I can just fill that in 120.91. And then, sorry, I always forget to do this when I'm doing mass percents. Okay, times 100. So we take the 12.01, we divide it by the 120.91, and multiply by 100, I get like 9.93%. If I do the mass percent of fluorine, I need to take fluorine's mass, which is approximately 19, and multiply it by 2. And again, I just divide it by the molar mass of the total. Like this is like we're finding the percentage of fat, we're finding the percentage of protein, and we're finding the percentage of, I don't know, skin or something like that in the body. So 19 times 2 divided by our 120.91, and we multiply it by 100, and this gives us 31.4%. One way you know that you've done these correctly, if you calculate for everything, is that all of these added together should equal what? They should equal 100%. Because we've calculated every individual amount. So if I add that 31 and I add it to the 9.93 and then that majority 58.6. No, I did something wrong. 31.4 plus the 9.93 plus the 58.6. I get 99.93%. That's close enough, right? Because there's a little bit of rounding. I mean, and that's mass percent. Does that feel kind of easy compared to what we were just doing? No? Yes? Yeah, a little easier. So let's do, I'm going to have you do a mass percent for one thing, just to practice. Let's go to our whiteboard. All right, let's say we have the formula, oh, I don't know, HBr. Hydrobromic acid. The kind of problems that come after these are most challenging. Yes, we will, and we're going to go over that. So going from a formula to a mass percent is much easier than going from mass percent to formula, but we'll make it happen. Okay, so I want you to tell me what the mass percent of hydrogen is and what the mass percent of bromine is. And then when you're done, add them up and make sure that they equal roughly 100%. I'll give you guys, I don't know, 2 minutes for that. It's not a huge calculation. Okay, so for hydrobromic acid, we want to find the mass percent for hydrogen. I'm going to take the mass of hydrogen, 1.01. I'm going to multiply it by how many I have. In this case, I just have 1. Then I need to divide it by the molar mass of hydrobromic acid. So bromine has a molar mass of 79.904. We add that to the 1.01 and we get a total mass of 80.912, something like that. We take 1.01 and we divide it by that 80.912. Oh, sorry, multiply it by 100. I'm sorry, I always do that. All right, move the decimal over 2. And I get like 1.25%. Hydrogen is so light. It's such a light molecule. That's why. So to figure out the mass percent of bromine, we're going to take the mass of the bromine, which is 79. Let's make sure I'm 79.9. Yeah, I thought there was a decimal there. 904, something like that. We divide it by the 80.912, multiply it by 100. We're going to end up with a pretty large percentage, 0.904 divided by 80.912. And I get approximately 98.75%. If I added these up, it's going to be approximately 100%. If you were like, well, there's only two things, right? And I know this percentage and I know it needs to equal 100, so I could subtract to get that. You can do that as well. But you can only really do that when you have two materials. If you have more than two, 3 or more, you've got to calculate at least for a majority of them. So any questions on going in this direction? No, okay. The other way is trickier, but it is definitely something that you all can handle. I know it. So we have gone from a chemical formula into the mass percents. We want to now go into mass percent or be given the mass percent and come up with a chemical formula. So I could say, hey, I've got like 55 grams of, carbon and like 22 grams of hydrogen and 8 grams of whatever. What's its chemical formula? Well, let's first reestablish some definitions about formulas. So there are two types of formulas that we're going to use in here. That's empirical formula and a molecular formula. So an empirical formula is not going to let me draw. Not going to let me draw. Okay, well, it is what it is. Well, that's why. So our empirical formula will always give us the lowest or the smallest whole number ratio of each type of atom in a compound. The molecular formula is always a whole number multiple of the empirical formula. So an example is hydrogen peroxide. This is the empirical formula. 1 hydrogen for every 1 oxygen, the lowest possible whole number ratio of the atoms. But what's actually happening in real space is this, and that's known as the molecular formula. It's really 2 hydrogens and 2 oxygens paired together. How do you come up with a molecular formula? Well, you take your empirical formula, which is your lowest ratio, and you multiply it by some value called n. N is just a whole number, 1, 2, 3, 4, whatever, that tells you how much bigger the molecular formula is than the empirical. So if you look here, this is twice as big as this. So our n value should be 2, right? I would take my empirical formula, which is HO, and I'd multiply it by 2 to give me H2O2. So let's say we've got C11, O22, H, hold on, guys. I don't like how I was writing that. C11, H22, O33. Is this an empirical formula or is it a molecular formula? Is it the lowest possible ratio? No. So we're going to classify this thing as a molecular. That means that this is what it really looks like if we were to examine it. It's really going to be 11 carbons, 22 hydrogens, and 33 oxygens. If I want to come up with the empirical formula, I need to divide everything by our lowest common denominator here, which is going to be 11, right? So carbon becomes 1, hydrogen becomes 2, and oxygen becomes 3. This would be its empirical. What is my n value for this? How many times bigger is this than this? It's whatever we divided it by. So it's 11 times bigger, right? If I was to take my empirical formula and multiply it by 11, I'd get back to that original molecular formula. So let's first spend some time talking about empirical formula. Because anytime I'm given the mass percent composition, I can go back to a chemical formula, but I specifically can solve for or go back to its empirical chemical formula, not its molecular chemical formula. So let's go ahead and do this for water. Let's assume that we have decomposed water using a battery. This is something you can do. And we end up with a separation of hydrogen gas and oxygen gas. And specifically, I get 3 grams of hydrogen and 24 grams of oxygen. How do I determine the empirical formula for this data? So I'm going to go to our whiteboard here. 3 grams of hydrogen and 24 grams of oxygen. We want to come up with a chemical formula for this. Now, I'm sure you all know what the chemical formula for water is, right? It's H2O. We're just going to prove that it's H2O. So, but let's say we didn't know what water was. We didn't know what H2O was. We just know that there's hydrogen with some sort of subscript X, and there's oxygen with some sort of subscript Y. So we want to figure out X and Y. How do we do that? All right, so the first thing to remember is that these formulas are a molar relationship. They are not a mass relationship. Why is that important? Well, because right now, these things are in a mass value. I don't want them in a mass value if I'm trying to come up with a formula. I need to get them into a mole value. This is not saying, hey, I have 2 grams of hydrogen for every 1 gram of oxygen. It's saying I have 2 moles of hydrogen for every 1 mole of oxygen. Okay, so if you're given something in grams, we need to get it into moles. This is another thing that's important. Sometimes you're not given things in grams. Sometimes you're given them in percentage. If you're given anything in percentage for these problems, what we're going to do is assume a 100-gram sample. And just cross out the percent and put a gram value there. And we will do one for that. But if you ever see percentage for one of these problems where you're trying to solve for the empirical formula, just assume a 100-gram sample, swap that percentage out for a gram. That will get you to your gram value if you're not there. Okay, so we're in grams. So first thing is to get it into moles. How do you do that? You use the molar mass. So 1 mole of hydrogen is equivalent to 1.01 grams of hydrogen, right? That's the molar mass. For oxygen, I need to use the molar mass for oxygen. So for every 1 mole of oxygen, it's approximately 16 grams of oxygen. And now we can figure out our mole value. So for this top one, and we're going to do some rounding with this, all right? So for this top one, this is approximately 3 moles of hydrogen. This over here gives us a value of about 1.5 moles of oxygen. So we have the molar relationship. For every 3 moles of hydrogen, we get 1.5 moles of oxygen. So the next step in the text/slides is to make like a pseudo formula where we use these as our subscripts. So hydrogen is going to get a value of 3 and oxygen is going to get a value of 1.5. These are the correct ratios, but why don't we like those? Why are they icky? Can you have 1.5 atoms of oxygen. So we want to preserve, keep the ratio, but we want to get it into whole numbers. So there's a quick way to do that. Divide each thing by the smallest decimal. So I'm going to take each of these and divide it by 1.5. Both of them need to be divided by the smaller decimal. Okay, so the 1.5 gets dropped under both. What happens to oxygen? Anything divided by itself is 1. 3.5 divided by 1, last time I checked, was 2. H2O. Oh my goodness, we just proved the formula for water. So the steps go, if it's percent, get it into grams by just assuming 100-gram sample, convert into moles, and then divide by the smaller decimal. If you still, after you divide by the smaller decimal, end up with decimals, I will show you what you do with that in a minute. But I want you guys to try one of these. Okay, so let's go with, just leave that up for now. I've got a worksheet in here that I like, and it has a bunch of example problems, and then it does have the answers. So if you want to do additional ones, you can. So let's do that very first one. It says, what is the empirical formula for a molecule that contains 65.5% carbon? Let me zoom in here a little bit. We're so far away. Okay, there we go. So we've got 65.5% carbon, 5.5% hydrogen, and 29.0% oxygen. 65.5% carbon, 5.5% hydrogen, and 29.0% oxygen. I'm going to go back to the whiteboard and I'm going to write those values down. (65.5% carbon, 5.5% hydrogen, 29% oxygen. Remember, if you see percentage, just assume 100-gram sample. We're going to just cross this out and put a gram right there for each of those. Okay, that's all I'm going to give you. I want you to solve for the rest of it. So move through the process and pair it up with what you did with the water. I'll give you guys about 4 minutes for that one. Okay, so let's come back together to look at this one. So this problem was a little bit different than the example we did at first because this one was given percentages, but again, no biggie, just assume that it's grams. So now I need to get out of grams and into moles because a formula, chemical formula, is a molar relationship. 1 mole of carbon is equivalent to roughly 12.01 grams of carbon, which ends up giving me 5.45 moles of carbon. The next one, I have 1 mole of hydrogen is equivalent to 1.01 grams of hydrogen. So we end up with 5.45 moles of hydrogen. I like this because this and this are the same decimal. So hopefully we end up getting something close. This one here, 1 mole of oxygen is equivalent to 16 grams of oxygen. And that equals 1.812 or 813 moles of oxygen. So then the steps say, hey, make a pseudo formula. You don't really have to make the pseudo formula. If you want at this step, you can just divide by the smallest decimal if you don't want to go through that. So what is our smallest decimal here? It is this 1.813. Sorry, that is a mess. 1.813. So I'm going to divide everything by 1.813, 1.813, and 1.813. All right, 5.45 divided by 1.813 gives me 3.006. That is close enough to be 3. Bam, 3 moles of carbon. This is also 3 moles, but it's 3 moles of hydrogen. And then this one, anything divided by itself, is going to be 1 mole of oxygen. So now you can write a formula. People will sometimes ask, oh, what do I put first? Whatever they give you it in, write it in that order. So I'm going to write the carbon first with a 3. I'm going to write the hydrogen with a 3. And then I'm going to write oxygen, and that has 1, so I'll leave the subscript off. Questions with that one? I'm going to have you do one more, because why not? This one, what's going to happen is we're going to get to this place here, and we're still going to have a decimal. So I want you to solve to that place, and then we will, I'll show you what to do next if this happens. So let's clear this out. You are going to be given 49.8 grams of sodium, okay? 113.6 grams of chromium, Cr, and 121.4 grams of oxygen. Okay, I want you to come up with the empirical formula. This is what you're trying to find. So follow the same steps that you did for the last 2 problems. Stop when you feel like you can't go any farther, and then we'll come back together. Give you guys about 3 minutes. Okay, so for this one, same process. We're given it in grams, so we don't have to assume percent gram, but we do need to go through that process of dividing by the molar mass. So sodium has a molar mass of 22.99 grams. Chromium has a molar mass of roughly 52.00 grams. And then oxygen, our good old oxygen, is that nice 16. So what I get here is 2.166. Okay. This one here is 2.185. I like that because those are really similar to each other. And then our last one is 7.5588. And this is now in moles of sodium. This is moles of chromium. And this is moles of oxygen. Next step, divide by the smallest thing. So the smallest decimal here is this one. So I'm just going to divide this by 2.166, divide this by 2.166, divide this by 2.166. So what I get is a value of 1 mole of sodium, 1 mole of chromium, and finally, 3.5 moles of oxygen. So the previous problems, we got whole numbers when we got to this step. I am now, I'm still in a decimal. It's definitely not close enough to round. You would never round unless you were at like 3.94 or 3.01 within a tenth. Otherwise, you're going to need to add one more factor. So what we're going to do is multiply all of these things by a number to get rid of that decimal. And there is a specific formula for that or chart for that. So if we go to this chart here on slide 49, you can see that if you're at 0.5, which is what we're at, we're going to multiply it by 2, right? Or if you have a decimal, that's a fractional subscript, that's a half. 2 gets rid of a half. 0.33, you'd multiply by 3, right? A third you get rid of by multiplying by 3. A quarter you get rid of by multiplying by 4. So use those in relationships to the decimals. So for our problem, we need to multiply everything by 2. You don't just do it for the thing that needs it. You do it for everything because you want to preserve this relationship. So I'm going to multiply this by 2, multiply this by 2, multiply this by 2. That means I have 2 sodiums, I have 2 chromines, and I have 7 oxygens. And this is sodium dichromate. Cr2O7 is a polyatomic ion. You're wondering where that's coming from. So you follow the same system. This one just had that extra step because after we divided by the smallest number, we still had a decimal. Are we good with that? Are we good with solving empirical formulas? Because next we're going to do the molecular formula. If you know the empirical formula, you figure out the molecular formula. Okay, so let's do it. So let's look at this formula here. CH2O. Is that an empirical formula or a molecular formula? That is an empirical formula. It is the lowest ratio that we can get between these atoms, 1 carbon, 2 hydrogens, and 1 oxygen. If I want to find this thing's molecular formula, I have to take the base empirical formula and I have to multiply it by some sort of whole number. And that whole number is going to be N. Hold on one second. I want to be able to draw on this. So I have my empirical formula here. And I multiply it by N. And N is just how much bigger is the molecular formula than the empirical formula. If N is 2, the molecular formula is twice as big. If N is 3, it's 3 times as big. How do you figure out N? Well, this is N. N is the molar mass, or specifically the molecular molar mass. And this is going to be solved experimentally, or, I mean, you guys aren't going to run an experiment during a test. So this is going to be given to you. They're going to say, hey, the molar mass of this thing is blah, blah, blah. What is the molecular formula? The empirical formula molar mass, you're going to calculate. How are you going to calculate it? Well, you have the empirical formula, right? It's CH2O. So you're going to take the mass of a carbon, the mass of 2 hydrogens, and the mass of an oxygen. Another thing to remember, it's always going to be big over little. Big divided by the little number. Because this needs to be a whole number. Okay, so if you may get them flip-flopped, you'll know because you end up with a decimal. We want a whole number. So if we're trying to find the molecular formula of this thing, let's go to the next slide. Let's say that the empirical formula is CH2O, but the molar mass of the actual molecule is this. It's 180.2 grams per mole. What is the molecular formula? Okay, well, my molecular formula is going to equal my empirical formula, CH2O times N. What does N equal again? N equals my molecular mass divided by my empirical. Remember, molecular mass is given to you. So in this problem, it's that thing right there. So we take that 180.2 and we're going to divide it by my empirical mass, which is the mass of this. So I take the mass of a carbon And I add it to a hydrogen. Well, I add it to two hydrogens rather, and an oxygen, and it should give me approximately 30, okay, 30 grams per mole. This is also a unit in grams per mole. So the units cancel and you're just left with a unitless thing. 180 divided by 30 is 6. You're done. No, not yet. Not yet. Okay. You need to take the 6 and you need to thread it back into this equation, right? Because the molecular formula is 6 times as big as the empirical formula. So I need to take this thing and take every subscript and multiply it by 6. Carbon will now get a new subscript of 6. Hydrogen will get a subscript of 12. And oxygen will get a subscript of 6. Okay? This thing is 6 times as big as this thing. That's where this comes into play. So let's go back to that problem that we were working on earlier. Okay. So we had established for this thing that was 65.5% carbon, 5.5% hydrogen, 29% oxygen, that our formula was C3H3O. If the molar mass of the compound from number 1, so this thing here, is actually 110 grams per mole, what is the molecular formula? So our molecular formula needs to equal our empirical formula. In this case, it's the C3H3O times some value N. I want you to figure out what N is. How many times bigger is it than the empirical? Okay, so I'm going to pull this information over to our whiteboard. Figure this thing out. So we said that we have C3H3O. That's our empirical formula. Sometimes the problems will give you the empirical formula. Sometimes you have to like solve for them like you did in my previous problem. Okay, so we've got our empirical formula. We want to figure out the molecular formula. And I know the molecular formula is going to equal my empirical formula. So the C3H3O times N. What is N? N is just my multiplier. How much bigger is my molecular than my empirical? So N equals molecular mass over empirical mass. Where is the molecular mass coming from? Remember, this is going to be given in the problem. So for our problem, it said it was 110 grams per mole. The bottom is empirical mass. That's coming from the empirical formula. So we need to take the mass of 3 carbons, add it to 3 hydrogens and 1 oxygen, and you should have gotten 55 grams per mole. Okay. Top is given, bottom you calculate. So this gives us an N value of 2. Or our molecular equation, molecular formula is twice as big as our empirical formula. So take the 2 and thread it back in here. This is now a 2. That's going to be C6H6O2. We now have a formula that's twice as big as our empirical formula. Questions on that? Juan, does that make a little more sense now? No, you had said that part seemed a little more difficult. Hopefully that is clearing it up. That's the end of the chapter. So you guys let me know if you want to go over another example, if you feel good with it. That worksheet, again, you can find in Moodle, this one here. there's a whole nother set of problems, and these are really great to practice empirical formula with the molecular mass to get the molecular formula. Stay away from the ones at the bottom of this worksheet, though. They're a little bit above your guys' pay grade. You may see something like this when you get into 151, but yeah, we don't need it now. So you guys stick to the top. So any questions? How do you feel about that chapter? I feel like it's a lot in that chapter. It's a lot of math. But really, if you can break it down into that flow chart and then those two last concepts, that kind of like encompasses everything. So good now. Okay, Juan, awesome. I'm glad to hear it. All right. Yes, the book emphasizes the importance of units after answers. Yes, it does. Okay, so is that important in mastering chemistry? Yeah, if you're giving a numerical value, you're going to want to have units. Sometimes the questions on mastering chemistry will give you the units. It'll say something like, you know, the numerical value you plug in, and then it'll say mole. So you know you're solving for a mole, but it doesn't always. So it just depends on the problem. But if they don't give you a numerical, or rather a unit, and it's requiring a unit, definitely put the unit in. Oh, like mole plus element symbol also. I would, I'm not 100% sure though. I'd have to like mess around with mastering chemistry. Yeah. All right, any other questions, comments? Okay, you have a lab due on Sunday, and you'll also have a homework due this Sunday. So just make sure you get to those. Your next test will be, I think it's in like 2 weeks, 2.5 weeks or something like that. So you've got a little bit of a break here. Great, I'll see you guys next Wednesday, unless you need to bump into me earlier. I'll be on campus or I'm around Monday. Otherwise, have a really awesome week/weekend. I'll see you next time. Bye, guys.